Okay, programming and debugging recitation. So how to make almost anything has been called how to almost make almost anything, or how to break almost anything. You'll find many ways to make things that don't work. And so there's two parts today. One is intro to programming, which you won't master this session or this week. It's a lifelong arc, but this is to get you started in just the structure of programming, and then handing off to Henk for the many ways things you make with electronics and microcontrollers won't work, and how you figure out what's going wrong. And so you're in the capable hands of Nicholas and Henk.
Okay, so I'll start with the first part. I will explain a little bit about microcontroller programming. The goal is not to give the course and programming before the course itself, but just to give you some advice and some overview about electronic and microcontroller programming. So the first thing you have to choose when you have to create some electronic device with onboard and programming system is to choose your microcontroller. And I will stress to choose your controller right, because I think that most of you will rush on RP2040 because it will be an easy module. You already created your CentOS version, which is based on RP2040, but there is many different families which are very dependent on your purpose, on what you want to do on your circuit, and then I will show a little bit first the different families that exist. The first thing you have to think of is how much processing power you need. Yeah, of course, you can always use RP2040 because it's very powerful, but sometimes you need less power for less power consumption. If you need to make something on batteries and so on, you actually need less power. You should also think about how much memory you need, about how much input-output pins you need, power consumption, as already said, and also existing libraries and support, because maybe some microprocessors are super good and super efficient, but there is very low support and libraries about it. If you're not able to write your own, it will be a blocking point. So the different Fab Academy families, I will say, are ATtiny, the smallest family. I'm a huge fan of, actually, because you can do already a lot with very small. And when I say small, it's both in terms of memory capabilities, but also about size. So you can do a lot with ATtiny. SAMD, which is a little bit more advanced, RP2040, I just talked about, which is on your CentOS, and ESP. So just let's first have a look at the different families that exist. So the ATtiny microcontrollers are very low-level microcontrollers. They are also low-cost. It means that you can have very cheap one, a very small one. Usually when the packages are small, it also means that the price is small. And they are suitable for very simple applications. It can also be very useful if you need different nodes on your circuit, and you don't want a lot of very high-end microcontrollers, but you want, for example, one, let's say, big brain, and different other nodes that are more specialized in dedicated tasks. For that, ATtiny family is a good candidate. Henk will talk a little bit more about that. But for each family, you have a way to program them, to actually program them. You have to connect something to the microcontroller, and then you have to actually send a code to the chip. And for the ATtiny family, it's a UPDI programming, which is interesting because it's only one wire. You only need one wire to send the information to send your program to the chip to verify it and actually to debug it, even though we are not very okay with the debugging right now. So it looks like that. It can be as small as just 8-pin small microcontroller. It's based on 8-bit cores, which doesn't mean that you can't do 16 or 13 or 32 bits calculation, but it means that it will actually use 8 bits, and it has to make some complex math to actually handle those bigger numbers. So the core actually is 8-bit, and you can go from about 1 megahertz to 20 megahertz. You can actually go lower, and as I stressed it before, sometimes going lower or at lower speed can be good for power consumption if you don't actually need all that computational power. They have very versatile input-output. It means that you can decide that one pin is actually an input or an output or a dedicated protocol pin, or it can be an analog pin. So you can really choose and configure the pin that and how you want it to act. So I already said UPDI is a single pin programming. I'm a huge fan of UPDI. I think that most of the microcontroller should actually go to UPDI. And to play a little bit with the ITtiny family, there is already a sandbox that was created by Adrian, which is called the Adrianino. So I put the link in the slide, so you can find the slide on the class website. But here you are, the Adrianino. Okay, so that was for ATtiny. Then you have the SAMD family, which is also from Atmel. They are much more advanced. It means that they work on 32 bits, and you can do much more complex things. But they are very complex. If you really want to program them from scratch, it's actually very difficult because the architecture itself is much more complex than the ATtiny architecture. To program them, you have to use SWD or JTAG, which is a subset of JTAG. SWD is a subset of JTAG. And the good news is that you probably already have a SWD programmer, as the CointerS is already able to make this. So the SAMD family itself, there are 32 bits. They can go up to 48 megahertz, which is pretty fast. They have an ARM Cortex core, which is high-end core and architecture. The most important things for SAMD family, I think, is the native USB support. It means that you can actually create your own USB device. It can be just something that you can change the program through the USB, but it also means that you can simulate a mouse, a keyboard, a mouse storage, or anything that can be on USB. So if you want to develop something that should be acting on USB, it's a good choice. It also has all the versatile input-output port as the ATtiny does, even though it's a bit more extended. And to play with, you already have something that exists, also developed by Adrian. It's just the successor of Adrianino, which is SAMDino. So exactly the same idea, but the main core is an SAMD instead of ATtiny. So after that, the new star is RP2040, which is created by Raspberry Pi. It's a dual core, no ARM, so it's even more powerful. Also with versatile, even though a little bit less versatile input-output capabilities. But the big star is because it has PIO, which means that you can actually program pins in a more complex way. You can put programs to the pins themselves. It's a little bit exaggerated what I said, but it's you can actually program on the very low level the action of the pins. And it's ideal for any project that will require very high-end and multitasking and connectivity and so on. So to program it will be through UF2, which is very easy because it's actually hard-coded. It means that you don't need anything. You just have to plug it to the USB and to make some boot sequence, and then you're able to put your file inside your chip, and you have nothing more needed. So as I said, it's 32 bits, still 32 bits, but you can go to super high frequency, at least for microcontrollers. It's 133 megahertz by native, but you can overclock it to 250 megahertz. As I said, I push a lot to underclock things, but if you really need power and you really need to go fast to do a lot of complex math, you can go up to 250 megahertz on dual core with quite complex microcontroller. So RP 2040 is really capable of doing a lot of things. Yeah, as I said, the bootloader is hard-coded. The good news with the hard-coded bootloader is mean that you can't break it. You actually always has access to the bootloader. And if you want to play and you need some sandbox, it exists because Adrian did create the Fab Xiao, which is based on the Xiao module containing the RP 2040, the same as you put on your CointerS. And last but not least, the ESP32, which is also an advanced microcontroller, 32 bits, made by Espressif. And you will use it more than probably if you actually need connection, Wi-Fi connection or Bluetooth connection, wireless connection. If you need it, probably you will go to ESP32, which is also very capable. It's based on Extensa, I think, architecture and RISC-V architecture, and it can go to 160 megahertz, so also pretty fast with very good wireless connectivity and still versatile input-output pins. And if you want to play with it, guess what? Adrian did create some basic sandbox, which is also the Fab Xiao, because the Fab Xiao is you have to choose which module you put on. Either you put RP 2040, either you put ESP32, and it will provide you the sandbox you need for playing with. Okay, there are other microcontroller that exist actually, but we use all the family we just said in Fab Academy. But just for you to know, there are also the STM32 families. PIC, I actually learned programming microcontrollers on PIC. I'm a huge fan of because of some very specialized peripherals. There is MSP from Texas Instruments and so on and so on. So there are a lot of other families, but for the Fab Academy, we consider essentially the four I just presented before. Okay, the main general rule, and I guess that Henk will stress it even more, LTFM, so I won't explain what it means, or at least read the data sheet. If you want to actually understand what's beyond and how your microcontroller works, go to the data sheet and read a little bit about it. It's very difficult to read the full document because it's hundreds of pages, but have a look at what you're interested in and just go to the manual to see how it actually works. So basically, yeah, for very small things, itty tiny, more advanced things with USB, go to SAMD. You need already package and high-end microcontroller, go to RP 2040, and you need connectivity, wireless connectivity, go for ESP. Now that you have your microcontroller, you'll need a language to program, to actually tell what you want to do. And then you have to choose a language. Just for your information, during the last bootcamp, instructor bootcamp, my own assignment was to test as many languages as possible on the RP 2040. So I just linked the page there. I won't go too much into details about what I did, but just, yeah, okay. I really tested different languages just for fun, actually. The first one, and I just put a matrix image because it's, yeah, the less accessible one if you're just starting, but actually it could be a good idea to learn a lot of, is when you try to program things directly. When I mean directly, I mean you speak your chip language, and that's assembly code. That's called assembly code. For each processor, you have a series of actual instruction that the chip understands. And writing a code in assembly means that you have to learn all the instruction that your very chip can understand and execute, and to write it like almost directly manually. that's called assembly code. As I already mentioned, PIO is very close to assembly code because it's actually a program that you will run directly on a state machine, which is very close to the pins of your microprocessor, typically on RP2040. And it means that you have to learn that very basic language. When I say basic, it means actually it's difficult to understand because it's a very machine thing. But yeah, I think I encourage you strongly to learn the PIO, and I think Neil will also. Just mention the VHDL and Verilog, but there are very specific languages to do high description language of what a circuit should do. You can use it to program. You can use it to create actually a microcontroller or a microprocessor or something. So I won't go too much into details, but those are the most I would say low level, but actually most complicated also language to learn. And they are very chip dependent, usually, assembly and PIO at least. Okay, so the most commonly used and that you will find in actually 90% of all the projects that actually exist on microcontrollers is C and C++, because it's a very old and very robust and with full libraries and quite close to the hardware and so on. So it's a very commonly used language. It's C and C++. C++ is just an extended version of C with some points I will explain a little bit later. If you know Arduino, just because you've heard of Arduino is based on C and C++. Then you go with the new star, which is Rust, and Rust is gaining a lot of popularity. It's much more recent. I think it was developed in Mozilla Research. And it's also a compiled language, just like for C or, yeah, also a little bit of assembly. You have to compile your code. You have to transform what you wrote to an actual machine code that you can send to the chip. And so Rust is also a compiled code. And yeah, Rust was invented to handle some mistake that you can actually do in C and C++, and with it will manage and get you cleaner code. I think it's the only language that was added to Linux so yeah, the new one, but it's growing fast, actually. Rust is gaining in popularity very fast. Then in another family of languages comes MicroPython, which is just Python for microcontrollers. And Python is much higher level language. It means that it's much more abstract, it's much more human, I will say. And that's something that people often like because it's easier usually to learn. And actually you can run it now on microelectronics. It will be interpreted. It means that it will compile your code as it's executing it, even though you can pre-compile actually Python. But so you can put a program on your chip which is Python or MicroPython, and then you can send actually instruction in Python to that chip that will actually interpret it and understand and execute what you just set to the chip in Python. I will show some example with it. And you can also use JavaScript, even on RP2040, which is also interpreted language. It was more used for the web, for web page and so on, but it's also gaining in popularity to microelectronics. So you can even use JavaScript to a chip. To be absolutely honest, I usually prefer precompiled code and lower level language because it's more adapted to material, because those microcontrollers doesn't have a lot of computing power. And it means that it's better to make all that job before sending it to the chip than making the chip interpret what you just said, because it's a lot of work for the chip. So it's usually more efficient to write directly in C or even more in assembly. But I will contradict myself in a minute. Something interesting is that you can sometimes mix the different languages. So you can take advantage of the best of each world. You can actually write assembly code in small section in your C code, and you can even write C code in C++ code, because C++ is just an extension of C. So you can actually write one program that will use C++, C, and ASM in the same program. But even more interesting is a new combination on RP2040 of Python and PIO, because actually Python, as I said, is a high-level language, so it's very human. It's very easy to understand and to make much more complex things in Python. But it requires a lot of power, which means that your two big RRM core will have a lot of work to do. But the good news is that they're able to do that, while for some stuff you need something more efficient, and that's where PIO comes. So here you have a small example that just a controller for a strip of LEDs. All the code is written in Python except, so that's very common and basic Python code, except a small section which is just for handling the pins of the RP2040 at a very specific time. And for that, you use something which is PIO. So you can mix Python with PIO and put the right amount of complexity where you need it. Okay, so now that you wrote your actual program, you explain what you want to do, you have to send it to the chip. And for that, you have different methods that essentially depends on your use family. And I already explained, UPDI is one wire that goes directly to only one pin of the chip. ISP, well, the old-fashioned way to do the ATtiny family, so that's for older, but now a little bit obsolete material. You can use SWD and GTAC for more advanced pin, and these require 3 wires. 3 wires usually means that you have less pins to do your project, even though I will show that you can a little bit handle this. That's when you want to send directly your program to the chip. It means you write your program, you compile it, and then you send it with wires to the chip. Another very common way to do stuff is to put a bootloader in your chip. And what's a bootloader? A bootloader is a very small section of code that you will send to your chip through either UPDI or SWD or something. That's just a small section of code that will make your microcontroller able to speak to the external world. And what is the external world? Is everything outside the chip. And usually you use it to communicate to a serial line. It might be either USB or more conventional UART, or it can be to use a flash memory or an EPROM or something. Computers basically work like that. They just wake up and they have no idea about who they are, and they just look for some external memories on your hard drive or on the network or something just to boot. They need to search in the external world the actual program. So that's exactly the same idea here. You can put a very small section of code into your chip that would just be enough to communicate with the external world, and then with that bootloader, you can load new section of code. And it can be used to execute them directly, or it can be used to store a new program into your chip. Okay. And as I explained before, UF2 bootloaders are now directly hard-coded inside RP2040, which means that you just have to connect your RP2040 to USB, and it has a small section of code that is able to communicate through USB. And so when you want to load a new program to your chip, you just have to connect it to the USB, and you can load this program through the USB. So you don't need dedicated hardware to program your chip. And the good news is that you already created one, as the CointerS is basically all of that, because the chip itself, RP2040, if you want to play with, use the UF2 bootloader. If you want to do UPDI to, for example, program an ATtiny, you can do it through the serial port, which is also available on your CointerS. And if you want to do SWD to program your SAMD family, there is also that capabilities on the CointerOS. You just have to load the right firmware to the RP2040. All of this was also possible because Alex Taradov created that small firmware that will transform your CointerOS into an actual programmer for any of those three bootloader techniques. Okay, so I did write a small section about Arduino because I think there is a lot of confusion, specifically for people that are not used to electronics. Because you will heard a lot of Arduino, but not everybody knows exactly what Arduino is. Arduino was at the very beginning a small project to help non-computer people or non-technical people to create stuff in digital electronics. But so it has become a lot of things, and everybody calls it Arduino. So when you say Arduino, you should ask, yeah, but what part of the Arduino? The first part of the Arduino was called Arduino Uno, was a first board that was developed. So it was a basic electronic card, which is just like that. That's Arduino Uno. That's already the version 3. And so that's electronics. That's a small board with electronics equipped with an Atmega 328. Which is now outdated. Honestly, don't use that. We are in 21st century, so we don't want to use them anymore. But when you heard about Arduino, sometimes it refers to that small Arduino Uno board. So it can be an electronic board, but it's much more a set of libraries. And by a set of libraries, I mean that's piece of code that will help you write dedicated code for your electronics that will prevent you from having to learn the whole data sheet of your microprocessor. It will provide you some functions that will ease the writing of your code without you to need all the details about your chip. So Arduino is also, when we speak about Arduino, it's also a set of libraries. So it means about codes that are already written for you. Okay, and there is also the, I show here a small example. I think it comes from Neil. For the ATtiny 412, if you write it as a very ATtiny code in pure C, you will write something like this. It's just something that will flip your pin. So it means that if the pin is high, you have to put it low. If the pin is low, you have to put it high. And to say that in pure C, for ATtiny, you have to say which such a complex code. So it means that you have to know, you have to write it to V port A, and you have to write it with pin 7. It's already actually simplified code, but yeah, so that's very pure C. And if you want to write it in Arduino, there are like functions which are digital read and digital write that are much easier to read for human language. The price to pay is that they are less efficient. If you look just above, I commented, Neil comment, sorry, you can go to 0.3 megahertz, while if you write it like directly as the material will understand it, you can go much higher. So it means that the cost when you write it like that, it's a little bit higher, but it's still reasonable. And that's Arduino. Okay, the digital read and digital write are very Arduino libraries that will help you to just write that, not taking care, is that a SAMD or is that an ATtiny or is that a RP2040? No one cares, you just write it like that, it will just work. Okay, but it means that it has to do some functions under to actually execute what you asked for. Okay, when you want to use Arduino, so that set of libraries for the chips I just mentioned before, you have to add some libraries and some board definition to the actual Arduino program. And so for each family, there is someone that did the job of making and translating all that basic functions to actually working functions for your chip. The good news is it already is already done. And I just put here a link with all the stuff you have to add to your Arduino program. And if you want, you just go to that slide and you click there and you have everything in the clipboard. So you can copy paste it directly to your Arduino and you will be ready for the 4 families for your Fab Academy journey. Okay. Arduino, as I said, is a program. It's also a development environment. So there is a program you can go on and you can type your program in it, and you can click to send your code to the chip and so on. So it's also an IDE, what's called a development environment. So that will run underneath all the Arduino libraries, but not necessarily for the Arduino Uno. It might be for any board, and probably one that you actually made. And if you want to use one of the 4 families, as I said, you have to explicitly add them to the Arduino IDE. Okay, just be aware, because I was in trouble. I wrote some code for in Arduino for previous circuits, and when I took them back 2 years later, I tried to program them in UPDI, and it just didn't work. And it took me like quite a time to realize it was because of the version of Arduino. So the older versions are more compatible actually with the family we will use. And even though the IDE version 2, which now exists, is better looking, easier, it has some cool features. The editor is much better, and so on. So yeah, the issue is that probably you will have to choose or even to switch sometimes between one or other version of Arduino. And that's what Arduino IDE 2 looks like. I have to rush a little bit because there's a lot of things to say today. Some advices about programming. For when you program, you can write a program that works, but you can also write a program that works and will keep working. And that's not always the same. So here are some basic advices about how you program in a good way, in an efficient way. The first thing is that you have to document your code. Document as you go, as you already heard before. It's always a good idea to explain what you do when you program it. And in every language, there is a special feature that lets you comment. So it means you write anything you want without impacting your actual program. That's actually a meme about that. So actually, you should use it to comment what you are actually doing, to even for yourself. When you will read back your code in years, it won't make sense anymore. So just to remind what you write, just comment your code. It can obviously be used also just to remove some piece of code without actually deleting them. So you can just comment some instructions to make it inefficient. As I already stressed, please choose the right processor for your need. Don't use RP2040 for everything, even though it's a very general microprocessor. It usually isn't required. So I keep stressing underclock when you can, and use smaller families that are good too. Write modular and readable. It won't change a lot the execution of your code, but it makes your code readable. If you put everything instruction by instruction, line by line, and just write like 3,000 lines of codes, and you have to just find how to change that section of code, you will be lost, and anyone else that will try to modify your things will just get lost. So please write in modular way. I wrote a very small example, that not a very high-end example. But if you want just to make a LED blink, you just put it high for 20 milliseconds, and then you put it low for 1 second. Okay, and then you put it high for 400 milliseconds, and then you put it low for the comment is wrong here, for 2 seconds. You could actually write it in a more modular way, which is not always a good idea, but sometimes you can make your code easier. You can, for example, write a function which is flip and wait, that we just change the pin state and wait for several amount of time. certain amount of time, sorry. So you can actually put your pin high for 20 milliseconds, and then you can flip it and wait 1 second, and then flip it, wait for 400 milliseconds, and then flip it, and then wait for 2000 milliseconds. And it will do exactly the same things, except that you can read much easier your code that way. Okay, you actually won't use it to flip a pin, but just to show you that you can make things more readable by cutting them into sections and functions. Don't push that logic too much, because each time you have to go to a function, it will jump, and you can create what's called a Stack Overflow. But basically, it's a good advice to make it as modular as you can. Write parametric. I keep stressing it also to my students, even for designs.
Sorry, Nicholas, just a time check. It's 9:36.
Yeah, I know. Henk told me he only needs 15 minutes.
Okay, good. Carry on.
Yeah.
And also, I want to note to the chat, there's some concern in the chat at the big step function of the challenge of all this new material. Don't worry. You're not meant to know all of this from scratch. And I'll talk more about this in the embedded class. You'll get starting programs that get you going, and you'll make small changes. And over time, you'll understand more and more. You're not meant to digest all of this in one sitting.
No, today is a lot of information. I'm absolutely conscious about that. So yeah, the other good practice is to write parametric. It means that you don't put too much information directly into your code. I'll show directly with an example. If you create some board and you connect a LED to pin, let's say pin 7, and you want to blink that LED, you can write something like this, which means that you put your pin in as an output, and then you digital write high, digital write low on pin 7. But it means that you will repeat that 7, 7, 7. And it means that, yeah, okay, you will put it to another board, which is not connected to pin 7, but to pin 4. And you have to change all the 7 into another number. So the good way is to write it more parametric, and also you put a delay of 200 milliseconds high and 800 milliseconds low. If you do so, you can write it like that. You put a define section before, you just define that LED should be number 7, period should be every second, and flash time would be 200 milliseconds. And then you define those parameters there, and then you use LED as the number. Each time it will read LED, it will read actually 7. It will just, the preprocessor will just transform your LED into 7. And so it will know that it's on pin 7. It means that if you want to put it on another board, which is connected to pin 4, you just change the LED here to 4, and you're good to go. Okay, I'm rushing a little bit. You can use classes, which is something for more high-end languages. In Python it exists in JavaScript, it exists in C++. That's called object-oriented. It means that you describe some virtual object. You write it in a more human way. You describe what a LED is and how what you want to do with the LED. You can blink it, you can flip it, you can put it on, put it off, and then you write functions that will do just what you need. And then you will forget about that, and you just use your own, let's say, library you just wrote, which is a class, which is a very efficient way to code too. Okay, about optimization, you can, speed a little bit your processor. I'm rushing, but instead of making your chip do complex math, you can pre-compute it on your computer and make it easier for your chip to understand. You just put numbers in a table, and they will find, for example, sine. If you want to program sine, you pre-calculate all the possible values, and you just look to a table what the sine of 3, 4, 5 is. I won't go too much into details. I just wrote it there. Sometimes you have to think about some arithmetic operations are very difficult for microprocessor. For example, if you want to divide a number, it's very complex. It took a lot of time to a processor to do so. You have some tricks, mathematic tricks that you can just use to make it simpler for the microcontroller. And using proper type, I mean, when you do store information, to use the right size for the information can be critical too, particularly on small processors. That's it for me. Yeah, I used XKCD, pinodes.org, and some AI like ChatGPT and Neil for my examples. And that's time for debugging for Henk.
Okay. Let's see. Okay, do you see my screen?
Yes, we do.
Okay. So now we are coming to the easy part of this hour. It's more about what you can do to when it's not working. So you make your first circuit board, you printed it, you stuffed it, and then it's not working. So then it doesn't work. So that's never an answer. So you have to look in exactly what you did. So you learned at electronics production that after you mill the board, you have to do a visual inspection. Do it again, so it won't hurt. Then look at the components. Are they soldered correctly? Are they the right ones? And are they in the right place? Don't jump to easy conclusions. So it's easy to assume that the problem is the most complex part of the system, but many times it's not the case. So you might all remember the sysadmin slogan, did you turn it off and on again? So that also comes into account here. So often it's a simple or overseen part that is the reason why your circuit board is not working. And you also have to keep in mind that you're the one that designed, milled, stuffed, and programmed the whole circuit. So there are a lot of places where things can go wrong. The time pressure can be a factor and jump to fast conclusions, but it's better to stay calm and to think of a step-by-step approach. Yeah, then we come back to another important thing in Fab Academy, write things down when you are debugging. Also, when you are debugging, it's not only because when you write things down, it helps you to explain what you did. So while explaining what you did, you might figure out what you did wrong. So easy, and so that's the bug. Then, yeah, this is a very nice book. So the Programmatic Programmer. It's a book not on programming itself, more on improving development processes in a pragmatic way. And I came to this book by this. And so besides writing stuff down, so you can also talk to the rubber duck. So it's called rubber duck debugging. It's quite common in software programming, but it also works in with hardware. So it's a way of debugging by articulating a problem in spoken or written natural language. Always carry around the rubber duck and debug what you did by forcing yourself to explain what you did step by step to the duck. You can also do it with to your instructor or to a student or to a friend. But one of the main advantages of a duck is that it won't judge you. Then don't panic. It's easy to get frustrated, but when you can't find the problem. But it's important to stay calm. If you get frustrated, you're more likely to make mistakes, and mistakes can make the problem worse. It's also important to remember that debugging is a normal part of the development process. It's not a sign that you're a bad engineer, so it's a sign that you're a good engineer. So you're building all these blocks, and so it's falling down. And so narrow down the problems. And so fixing a bug that is not a bug, and so leads to new bugs. That was not a bug. And you don't want to end up in a situation where you trace the whole project because you can't localize the bug. That wasn't the bug from the beginning. So stay calm. So that's the same issue, narrowing down the problem. Reproduce the problem. Always do visual checks, traces, solving, components. And then keep in mind that the problem might not be visible without a microscope. So here you actually see a microscope and you see some floating pins. That were the bug, so the fault in the circuit. Concentrate only on the relevant parts, so isolate the problem. When a microcontroller is not receiving voltage, so these parts might be the problem. So one is the USB end, and then it's the voltage regulator. So if the microcontroller is not getting voltage, so only this part, so you probably will solve the problem. If you can't program a microcontroller, so your board is powered, but you can't program it, then narrowing down, so what's the programming part for the microcontroller, and it's actually a really small part of the board. When you get it programmed, so it's powered, you can program it, but you're unable to program another microcontroller. You probably end up somewhere here, so on the second part of on the other part of the microcontroller. So this is actually it's a programmer, or no, it's an FTDI. It's an FTDI board. So now we go to hardware tools you can use for debugging. One is the multimeter. It's a hardware tool that can be used to measure two or more electrical values, usually voltage in volts, currents in amperes, and resistance in ohms. Multimeters are great tools and one of the most fundamental pieces of test equipment. They can be used to debug electronic problems within an embedded system. It's used many times as for continuity. I made a sample here. Okay, it's not doing audio, but so normally it beeps. So when there's a connection, there should be a connection here, not on the other places. It beeps. But you can't hear it, so I'm gonna pass this one. Here you can see a voltage drop. Let's say so this microcontroller needs 3 volts. You see that blinking all the LEDs. Okay, I continue. So what you see here is a voltage drop, meaning that the voltage goes below 3 volts, which might mean that the microcontroller is underpowered at certain moments and might fail. Then here we have a logic analyzer. So it's a hardware tool designed specifically for capturing, displaying, and measuring electronic signals in a digital circuit. This tool consists of several digital input pins capable of detecting whether an electrical signal is at a specific logic level, so at 0 or 1. You saw it very nice here. So let's see. I can go back. Yeah. So it's not measuring the actual values, but it's measuring as though if it's on or off. And here you see the transcoded message. So logic analyzers are also capable of showing the relationship and timing of different electronic signals and digital circuits in a digital circuit, and often capable of also analyzing digital communication protocols like UART, I2C, SPI, or one-wire protocol. Logic analyzers can be used to debug hardware, software, and firmware. So this is a sample of the bits that are floating through the pins. You see the RX, the TX. So this is the TX, this is the RX, and these are the decoded signals. So it's hello world. So we share the slides afterwards. So logic analyzers are quite cheap, and here are the links. And what's important is the microhooks to connect your logic analyzer to the boards. This is a portable logic analyzer from Miniware. That's pretty good to know. Then an oscilloscope is a hardware tool that graphically displays electrical signals and shows how these signals change over time. In this video, it's showing a blinking LED. The oscilloscope is connected to the ground, and the LED is blinking at the interval of 1 second. And here you can see it so on the oscilloscope. So these are the beautiful hands of Dua. Dua is here, I think. But here you can see, so it's actually, so here, 1 second. It's 1 second off, 1 second on. And you see doing the same with the button. So normally oscilloscopes can store signals in memory. So what Dua is doing here is that she travels through time, go back in time to show the actual signal, so you can better research the signal. Okay, radio communication. This tool actually is a DVB-T USB dongle, but with the right software you can use it for wideband software-defined radio together with, for instance, GNU Radio. It's an open source project. It's great, and you can use it for debugging your wireless projects. This is a video. Because of time, I'm gonna skip a lot, but what it shows, probably we'll go a little bit further. And so here it's getting in the signal. Here you have a waterfall, but what we actually want is to see the digital information that's going over the airwaves. And Yeah, we're almost there. Yeah, here you see the bits going by. So it's a nifty tool. So all these tools are very cheap. So they are affordable. So logic analyzer doesn't have to cost you a fortune. So somewhere between 30 and 100 euros. So it's more than enough to get a decent logic analyzer. Then for flashing board and what can go wrong. So this is a video that doesn't work. Okay, this is how you program some Ds and other boards. So this is the programmer, the SWD programmer.
Sorry, I'm just going to interrupt briefly. I have to run to a 10 o'clock meeting, but you can keep going. Nicholas, I'm going to make you the host.
Okay.
And so you can stop recording.
Yeah, we'll try.
Okay, thank you, Henk and Nicholas, and see you all on Wednesday.
So these SWD JTAG connectors have standard of 10 pins. You see the pins. They are a little bit smaller than the regular pins we know. So the 2.45, 54 millimeters. So this one is 1.27 millimeters. But you have to be aware of the orientation of the pins, and you have to be aware of, and that you actually have to look up in your data sheets. So where the voltage is and where the ground is. And you have to make sure that in this case, that the programmer is 3.3 volt. Because if it's 5 volt, so you're going to trace your SUBD microcontroller. UPDI, Nicholas already talked about it. It's very simple. So it mixes the RT and the RX and the TX signal with a 4.7, so in this case 4.9, almost 5 K resistor. Then what you can also do is serial debugging. And so define debug modes in Arduino, IDE, or in C. And you can print debug signals to your terminal. Or, yeah. And then again, of course, so read the fucking manual. There are always reasons why you don't want to spend your time in reading manuals, but also it makes sense. So it's not the purpose that you have to read all 1,000 pages, but so you need to understand where you can find the information within the manual. So read the fucking manual. And don't give up, so don't panic. And these were my slides. Okay. Are there any questions? We're just in time, Nicholas.
Yeah, indeed. Just as a comment, especially for the people not used to electronics, that's the first time that we give the course about programming, not the first time that we give the course about debugging. It was usually after the electronic production and programming. It was with Francesco and Dua before. It's normal if you feel a little bit lost. Electronics will be a big part of your Fab Academy journey, so it's normal that you have still a lot to learn. We didn't even start the programming courses. They're just, general advices. Don't hesitate to come back to that recitation after you learned a little bit more, if not used to electronics. Hope it helps. Don't hesitate to provide us with comments for the next years. The slides are available in the class website Git for those who ask. Otherwise, just ask us. We will send them. And if there is no more question, I think it's time to leave. Thanks, everybody.
Bye.
Yep.
Bye.
Push it down.
Bye bye. Tack för ikväll. Very good.